Now, let's solve the 28th and final quiz of the semester. I hope you all enjoyed my quizzes. I hope it was good preparation for the exams. Remember, why am I giving a quiz every time in this course, in this lectures? Because I want you to think about the subject at hand, okay? I could keep on lecturing for hours and hours, and just sitting there passively listening to my lectures is never useful. The only way to learn about a topic is to think about it. My lectures are useful to the extent that I make you think about the subject. And within a week's time, we'll see how much we have accomplished that goal in your final exam. So today, let's solve this quiz, then do a review of what we have learned since the second midterm. And that'll be the end of the course. All right? Good. Now, here's an electromagnetic wave. This last chapter is a little bit strange. It's different from the other chapters. In all the other chapters, we actually asked you to get to some results starting from some very basic equations like Gauss's law, like Faraday's law. It starts from something very simple, but ends up in applying it to a complicated system. Now, in this last chapter, you don't have the mathematical tools to go from Maxwell's equations to the properties of electromagnetic waves. Which tools are you lacking? You don't know enough vector calculus. You don't know enough differential equations. Don't worry, you'll learn about them in a few years. Now, maybe you won't, okay? So now, then what do we need to do? We actually need to remember, if you want, memorize some of the results regarding electromagnetic waves. Now, first of all, here I'm given the electric field E0 3I hat plus 4J hat times sine. And I'm going to write this a little bit differently. 2 pi over 3z plus 2 pi 10 to the 8 t. Now, which way is this wave? OK, first let's answer the first question. What's the frequency? What was our general rule? Our general formula was for the electric field component of an electromagnetic wave. I had cosine k z minus omega t. Okay? And omega is then the factor in front of time. So what's the frequency here? This 2 pi times 10 to the 8 is omega. Frequency is 2 pi, well, omega divided by 2 pi, angular frequency divided by 2 pi. So this is going to be 10 to the 8 hertz. How many of you wrote this down? OK, good, great, excellent. I'm thinking you haven't done much else, but so. Yes?
We have a minus sign in front of omega in our general equation.
That's very good. That's a good observation. Now, the way we defined omega is, it's always going to be positive, okay? Because it's basically a rotation frequency, okay? But that's going to come into play. Now, obviously, sine, and here, why am I saying this wave is traveling in the positive z direction? Because I can write it as follows. I can write this as E0 cosine k z minus omega divided by k t. And what's omega divided by k? It's always speed of light, c, right? Omega is ck, so this is c. So this wave is basically, at time t, instead of z, I can say this is z minus z0 of t. So basically, my wave is moving in the positive z direction. The zero of my coordinate system is shifting in the positive direction as time goes on. Okay? This is a simple shift of the full wave with the speed c. But here, first of all, let me write this in another way. Let me write this as E0 3I hat plus 4j hat. Now, this is sine 2 pi over 3 z. And I'll do the following. I'll actually write this as z plus 3 10 to the 8 t. Okay? Does that make sense? Of course it makes sense. This is 3 10 to the 8. These numbers were not randomly chosen. This is the speed of light. But which direction is that changing? This is z plus z0 of t. So basically my coordinate frame is going into the negative direction. I am actually taking all of my function and shifting it to the negative direction. So this wave is moving towards minus z hat. Or you could also say direction of motion is minus k hat. Right? Now, in part B, I need to find the magnetic field component. Right? How do I do that? I know that if my electric field is given as E0, what was it? 3I plus 4 plus 4j times sine 2 pi over 3z plus 2 pi 10 to the 8. So what do I know about the magnetic field? I know that here I'll have some vector B0. The sinusoidal part, the part that's oscillating, is exactly the same for the electric field and the magnetic field. So I can just write sine 2 pi over 3z plus 2 pi 10 to the 8t without any problems. But now, how do I determine the vector B0? I had two rules. First, the direction of electric field cross the direction of magnetic field gives me what? Gives me the direction of propagation. In this case, it's going to be minus k hat. Okay? So magnetic field is perpendicular to minus k hat. Magnetic field, electric field, and direction of propagation were all perpendicular to each other. So, which means magnetic field has no z component. I can write it as bx I hat plus by j hat. Magnetic field must also be perpendicular to the electric field. Right? All three are mutually perpendicular to each other. So let's calculate this. Here, what does that mean? B0 dot E is 0. So I have bx I hat plus by j hat dot, what's the electric field vector? 3E0 I hat plus 4E0 j hat. That must be 0. So 3E0 bx plus 4E0 by must be 0. In other words, E zeros can cancel. Bx must be minus 4 over 3 by. Okay? I have one more constraint. What's my constraint? I've made sure all three are orthogonal, but so I'm going to say B is just writing Bx in terms of By minus 4/3 By I hat plus By j hat. So what's E cross B now? E cross B. This is going to be E0. From here we can see it's 3I hat plus 3I hat plus E0 for j hat cross minus 4 over 3 By I hat plus By j hat. Now I'm looking at the cross product. What's the cross product of I hat with I hat? Come on, guys. It's the last lecture of the semester. What's the cross product of any vector with itself? 0, right? Dot product is the length. Cross product is 0. Any vector crossed with itself is 0. What's the cross product of I hat with j hat? I hat cross j hat gives me k hat. Exactly. Right? So it's going to be 3 E0 By k hat. And how about, again, j hat with j hat gives me 0. So I had now j hat I hat. And what's this going to give me? It's going to give me minus 16 over 3 E0 By k hat. Or in all other words, it's going to give me 9 minus 16 is minus 7 over 3 E0 By k hat. It must give me some vector in the k hat direction. That's good. Question.
It should be plus 16.
Why do you think that?
Because j hat cross I hat it gives minus k.
Excellent. J hat cross I hat gives me not k hat, but it gives me minus k hat. There's another minus sign here, so it should be plus, which is going to be give me something even better. It's going to give me 25 over 3 E0 By. But you see, something is strange here. E hat cross B hat should give me propagation direction. And here it gave me positive k. It should have given me negative k. So I know that if I find two solutions for By, I must get the solution which is negative. Right. Let's keep doing. I still have not found what's the value of magnetic field. I had one more rule. What was that rule? The strength of magnetic field divided by the strength of the electric field is, well, it's just the reverse. It's just electric field is C times B. So basically what I find from here, what's the strength of the magnetic field? Here, B vector, the magnitude of B is 1 plus 16 over 9 square root By, or 25 over 9, or 5 over 3 By. So 5 over 3 By magnitude is strength of E is what? E is 4 plus 3I 4J. So it's going to be E magnitude is going to be 5 E0. divided by 5 E0. In other words, By is magnitude is 5's cancelled 3C times, that's wrong, 3 over C times E0. If this is the magnitude, I know that By must be negative. It must be minus 3 over C E0. Now I can write everything nicely. B of t is, what was it? I already wrote it here. Minus 4 over 3 By I hat plus By j hat times sine. Let me just write it as kz plus omega t. Now I'm putting everything in its place. Minus 3 over c E0 minus 4 over 3 I hat plus j hat, or maybe I can write it as minus E0 over c minus 4 I hat plus 3 j hat sine kz plus omega t. That's the magnitude. What's the final question? Find the magnitude and direction of the pointing vector. Can anyone tell me what's the direction of the pointing vector without any calculations? The direction of the pointing vector is always the direction of propagation. Okay? What was the pointing vector? What did that vector signify? It showed me which way energy was flowing, which showed me which way momentum was flowing. It was the vector which is going from the source to the absorber, right? So C pointing vector is 1 over mu 0 E cross B. So I'll just write 1 over mu 0. I have the expressions for everything, but I have already calculated what E cross B is. It's going to be 25 over 3 E0 By in magnitude, and the direction will be minus k hat. And I have calculated what E0 and By are, so I'm not going to do any more calculations. The direction is minus k hat, the magnitude is just 1 over mu 0, 25 over E0 By. Okay? That's all I need. Any questions? So, this is a good place to start our review. And as always, I will actually do my review in reverse chronological order. The last thing we have studied was electromagnetic waves. What do you need to remember before you go into the exam about electromagnetic waves? You need to remember the properties we have actually used to solve the question here. If I have the direction of the electric field and the direction of the magnetic field, E cross B magnitude gave me the direction of propagation. Furthermore, the magnitude of the electric field divided by the magnitude of the magnetic field was the speed of light. Furthermore, the electric field and the magnetic field had these vectors which satisfied these properties, but they also had the same sinusoidal dependence. The magnitude of k, which was called the wave vector, was just 2 pi over lambda, and lambda is the wavelength. Omega, which is 2 pi times frequency. These two things are not independent. Lambda times frequency is the speed of light. What's more interesting is that the speed of light is actually connected with the two constants we have learned, one from Ampere's law, the other from Coulomb's law. So we know that light is actually made up of electric and magnetic fields. Okay. We have learned one more definition, something we actually had to keep in mind. This vector, called the pointing vector, signifies the direction of energy transfer. What is basically, let's talk about the units of S. It tells us how much energy is flowing per unit area, per unit time through a given surface. So the units should be joules per second per meter square, and if you work out the units, that's exactly what you will find. Okay? Now, how did we come to this nice solution of Maxwell's equations? And why did Maxwell find it and not anyone else? There was Ampere's law, there was Faraday's law, everyone knew about Gauss's law. The critical thing Maxwell did was he understood those equations are not complete. So he added one term. So let's remember what Maxwell's equations were. First of all, we have Gauss's law for electric field, which told me total flux over any closed surface is related to total charge inside. We also have the same thing for magnetic fields, but no matter how much we actually look for them, we have never found magnetic charges yet, magnetic monopoles, so this is exactly 0. Now, we know that if I go around a loop, in a static situation, the potential difference is 0. But if there is a magnetic field that's changing in time, that induces electric fields, so these are called, this is called Faraday's law. The induced potential along any loop is proportional to time derivative of the magnetic flux through that loop. And the minus sign in front also got another name. That was the cheapest law you could find. That was called Lenz's law. Great. And if I do the same thing, B dot dl, already Ampere knew that that was mu0 times I in. But what Mr. Maxwell did is he added one more term. He said there must be a term proportional to the flux, electric flux through the surface for which this integral is evaluated at the boundary. Okay, and this was called displacement current. Right? And why did it change the character of these equations? Previously, only change of magnetic field could create electric field. But now when I actually add this term, I can get a feedback. I can get these equations basically inducing each other, and I can get electric and magnetic field without any charges or currents around. Okay. Good. So one standard example would be to take a circular capacitor. I can give you the current as a function of time, and I can ask you, what's the magnetic field B of t inside the capacitor? I think we've solved an example pretty much along these lines, so I will not solve it again. But that's the standard example. Please solve at least. There is a solved example in your book. At least go over that. It's better if you actually solve it. But that's one of the standard examples about displacement current. Good. Good. Now, what else did we learn? We've actually looked at AC circuits. And we have looked at three kinds of circuits elements, R, L, and C. And for all these three, we had a new definition. Everything was working like a cosine, right? It was sinusoidal. So we said all V's will look like this. All currents will look like this. Now, I'll define something new. I'll define Z, which was called impedance. It will be the magnitude of V divided by magnitude of I. And here, for the resistor, it will be just R. But for capacitor, it will be different. It will be 1 over omega C. And for inductor, it will be omega times L. Furthermore, I know the basic definition of my basic defining equation for both my inductor and my capacitor. Here, V is equal to IR. Here, I is C dV dt. And here, V is L di dt. So, one way to remember this is, for the inductor, I leads V. For the capacitor, V leads I. Okay? If you are not sure, you do the following. You don't try to memorize this. You just do the following. You say, hey, if my V is V0 cosine omega t, my I is apparently C times dV dt, which is going to be C times V0 times minus sine omega t. But minus sine omega t, I can always write as cosine minus cosine omega t minus pi over 2. And this minus sign I can actually change. So make it cosine plus pi over 2. So I leads V in the capacitor. It's just the reverse for the inductor. Okay? So you could solve any circuit by thinking about what was called phasor diagrams. If I know that there is a current phasor, voltage across the resistor will be in the same direction. I've just told you that current leads voltage for a capacitor. Voltage of the capacitor will be leading. It's 90 degrees forward to the current, and voltage of the inductor will be lagging the current. All in all, there was something that's really important. If I had R, L, and C circuit that is tied to an AC source, I have the phenomenon of resonance, which told me that the maximum current will flow as a function of frequency at omega 0, which was the natural frequency of oscillation of this circuit, okay? Which brings me to the discussion of the LC and RLC circuits. What did we learn about the LC circuit? If I have an LC circuit, there is no way for energy to dissipate in the system. So what will I find? I'll find all my currents and voltages will oscillate in time. What will be the angular frequency of oscillation? It will be square root of 1 over LC. Energy could be stored either in the capacitor. Energy in the capacitor is 1/2 Q square over C. Energy in the inductor is 1/2 L I square. So I will go from situation where there is no current running in the circuit, everything is stored inside the capacitor, to the situation where there is no charge on the capacitor, but there is a lot of current on the system. I'll just have back and forth oscillations of this system, okay? And here, actually, we have learned to solve one differential equation. Well, not really. We've seen that if I have an equation like this, okay, at the end of the day, f could be I or q. If I have such a simple differential equation telling me if I take two derivatives of a function, I get minus a constant times the function, that function can be either cosine omega t or sine omega t and nothing else. All right. Now, what happened if I actually added a resistor, which is obviously more realistic, R, L, and C? The only thing we need to remember is that now I still have oscillations, but all my oscillations die out in time. Why? Because energy is being lost on my resistor, and the energy loss will be with a time constant which was with L over R, okay? Now, which brings me to RL circuit or LR circuit. And what was the nice thing about inductors? Why did we like or use inductors? We liked them because they actually resisted the change in current. Okay, so if you don't want your currents to jump, if you don't want your currents to act fast, you put in a inductor to your circuit, because the voltage across an inductor is proportional to the derivative of the current through the inductor. So, for example, if I have the following circuit, if I close my switch at time t equals to 0, I will finally go to my limiting current V over R as a function of time, but I will reach there exponentially again with the time constant. I'm saying that this I will be V over R 1 minus e to minus t over tau, where tau will be L over R. Okay, so the higher yes, well, the higher inductor you have, the larger tau you will have. Okay, it will get there more slowly. Is it L over R or R over L? Is it L over R or R over L? Good. Now, what else? What else? I mean, we did it for the previous exam. What else did you learn? Another time constant for the. Let me quickly remind you. For the RC circuit, what was? Tau was R times C. What happens if I multiply these two together? I'll find tau at least units-wise square is L times C, or 1 over tau units, which is hertz, would be 1 over square root of LC. So it's actually nice to remember that these three formulas are connected to each other. Okay, time constant of the RL circuit, oscillation frequency of the LC circuit, and time constant of the RC circuit. All right. Good. What else did we learn? Where did this formula V equals L di dt come from? It came from induction. Okay. And what was our rule about induction? The rule about induction, or we called it Faraday's law, it said for any loop in space, there is always an induced voltage if there is a change of flux through the system. So for any kind of, I'm making up some loop, okay, I don't know what this is. If a current is running through that loop, there will be some magnetic field going through that loop, phi. And I know that phi will be proportional to the current running through my wires, and the proportionality constant will be inductance. So if I take a time derivative, my EMF, my voltage will be d phi dt, which is going to be L di dt. This inductance was sometimes called self-inductance. If I had, on the other hand, if I had, for example, two loops, I can run current in the first loop, and that is going to cause some flux to go through the second loop. Phi 2 will be proportional to I1, and proportionality constant will be called mutual inductance. You should be able to calculate, as your standard examples, the inductance of L of a solenoid or a toroid, or simple configurations like what happens if I have one solenoid. Well, I'm getting lazy. Let me try to draw it better. If I have one solenoid that is encircled by another solenoid, what would be the mutual inductance between these two solenoids? Okay. So I think if you go back, the final thing, well, it's basically a restatement of what we have said. For any loop, if I have any loop, it doesn't have to be a circular loop, of wire, I can say the EMF is d phi b dt through this loop. So there will be an induced current if I change the flux through it. There was a minus sign which told me that, as Monsieur Lenz said, Lenz's law was what? The loop always resists the change of flux. So you should be able to use this to find the direction of current. And because phi B is essentially B dot dA, there may be different ways of inducing currents. Magnetic field magnitude may be changing. The area can be changing. Right? I may be making my loop bigger, smaller. Or the dot product is B A magnitude cosine theta. This may be changing, which would be rotation of the magnetic field or the loop with respect to each other. So all these three cases would cause a change in flux, which will cause an induced current in our system. You should be able to handle all the three cases, at least simple examples of the three cases of induction. All right? So I think that's pretty much what we have learned since the second midterm exam. Now, please try to go through as many questions in the selected problems I've assigned. You don't have much time until the final. I hope you'll do better than the second midterm. The first midterm was okay. Second midterm, the class average fell by 12 points. That's not very good. I'm hoping you'll do better on the final.